In this video, we will explore the naive Bayes algorithm, a simple yet powerful classifier based on Bayes' theorem. Bayes' theorem is the foundation of naive Bayes. It calculates the probability of an event based on prior knowledge of conditions, where P of a given B is the posterior probability, the probability of event A given that event B has happened. P of B given A is the likelihood, the probability of event B given that event A has happened. P of A is the prior probability, the initial probability of event A occurring. P of B is the evidence, the total probability of event B occurring. Hypotheses, possible outcomes in the sample space, denoted as E1, E2, up to N. Prior probability, P of AI is the initial probability before new data. Posterior probability, P of AI given A is updated probability after new data. Conditional probability, P of a given B is the probability of a given B. Joint probability, P of A and B represents the probability of A and B occurring together. Random variables, variables determined by random experiments. The naive assumption states that features are independent given the class. This simplifies computations while still being effective in many cases. Let's see an example. Spam classification. Imagine we have emails, and we want to classify them as spam or not. Consider two emails. One is a spam email saying, "Free offer, win a prize, single quote," and another is a normal email, "Meeting reminder for tomorrow." After applying Bayes' theorem, we determine that the most likely classification is spam. In conclusion, naive Bayes is a powerful and efficient algorithm, especially for text classification tasks. Despite its simplifying assumptions, let's understand naive Bayes classifier with a spam classifier example. Here is a sample dataset containing words and we want to classify an email as spam or not spam, based on the presence of certain words. We calculate the prior probabilities of spam and non-spam emails. Now, let's compute the likelihood probabilities using Laplace smoothing. Here are the computed likelihood probabilities for each word given spam or not spam. Now, let's classify a new email containing the words free, WN, and money. We compute the posterior probabilities for both spam and not spam. Since the probability of spam is higher, we classify this email as spam. Final decision: this email is classified as spam. Naive Bayes is a family of probabilistic classifiers based on Bayes' theorem. It assumes that features are independent, which simplifies computation. There are three main types: Gaussian, multinomial, and Bernoulli naive Bayes. Here is a table showing the different types of naive Bayes classifiers and their applications. First, let's look at Gaussian naive Bayes. It is used when features are continuous and normally distributed. For example, predicting a flower species based on petal length and width. Next, we have multinomial naive Bayes. It is used for text classification problems, where word frequencies matter. For example, determining whether an email is spam based on word occurrences. Finally, Bernoulli naive Bayes. It is best suited for binary features, where features take only 0 or 1 values. A good example is sentiment analysis, where a sentence is classified as positive or negative based on word presence. Naive Bayes classifiers are powerful for classification tasks, especially when working with text and structured data. Each type has its strengths. Gaussian for continuous data, multinomial for text, and Bernoulli for binary features. Despite the assumption of feature independence, naive Bayes performs well in practice. Naive Bayes is a probabilistic classifier that is widely used for classification tasks due to its simplicity and efficiency. One of the most well-known applications of naive Bayes is spam filtering, where it classifies emails as spam or not spam based on words in the content. Naive Bayes is also used in sentiment analysis to determine whether a text has a positive, negative, or neutral sentiment. In the medical field, naive Bayes is used for disease prediction based on patient symptoms and medical history. Naive Bayes is also applied in medical document classification, helping in sorting and categorizing medical records efficiently. Let's explore the advantages and disadvantages of the naive Bayes classifier. Here is a table summarizing the advantages and disadvantages of naive Bayes. Naive Bayes is extremely fast, even on large datasets, because it simplifies probability calculations. However, its assumption of feature independence may not always be valid. Naive Bayes can handle missing values well, making it robust for real-world data. However, categorical features can sometimes cause accuracy drops if not properly pre-processed. Naive Bayes is simple and easy to interpret, making it useful for explainable AI. However, its probabilistic assumptions can be too simplistic in certain scenarios. Naive Bayes performs well with small datasets, unlike complex models that require more data. However, it struggles with imbalanced class distributions, which can bias predictions. Naive Bayes excels in text classification tasks like spam filtering and sentiment analysis. But it has difficulty capturing complex relationships between features, limiting its use in certain applications. This concludes the discussion on the advantages and disadvantages of naive Bayes. Naive Bayes is a probabilistic classifier based on Bayes' theorem, often used for text classification and spam detection. Let's explore its working, advantages, and limitations. Here is a summary table highlighting key aspects of the naive Bayes classifier, including its assumption, formula, types, strengths, and weaknesses. First, the naive Bayes classifier makes a strong assumption that all features are independent, which is rarely true in real-world data. The fundamental formula is based on Bayes' theorem, where the probability of a class-given input features is determined using prior and likelihood probabilities. There are different types of naive Bayes classifiers. Gaussian for continuous data, Multinomial for text classification, and Bernoulli for binary data. It is widely used in text classification, spam filtering, and sentiment analysis due to its efficiency and simplicity. Naive Bayes is fast, requires less training data, and works well with high-dimensional data, making it suitable for real-time applications. However, its assumption of feature independence can lead to incorrect predictions when features are highly correlated. To improve performance, it is recommended to use feature selection, Laplace smoothing to handle zero probabilities, and appropriate handling of missing data. In conclusion, naive Bayes is a simple yet powerful algorithm, especially for text classification. Despite its unrealistic assumption of feature independence, it performs well in many real-world applications. By carefully selecting features and applying techniques like smoothing, it can be effectively used for classification tasks. I hope you found this video helpful. If you enjoyed it, please give it a thumbs up, subscribe to the channel, leave a comment, and share it with your friends. Your support means a lot. See you in the next video.